Okay, students. In last class, we had some discussion about types of relays and some basic terminology related to relays, and also we had a discussion about some type of relays like electromagnetic attraction type relays, and those relays we can saw the solenoid type relays, that means attracted armature type and balanced beam type relays. Okay, and also we had seen the advantage and disadvantage and applications of those type of relays. Okay, like this. So one more, and also we had seen some terminology related to relays, like what is operating time, what is restraining, that means operating time, what is operating torque, and what is reset value, and also we had seen some basic things like other name of reset time is a dropout time, and pickup current, what is a pickup current, and also we had seen reset time. Okay, we've seen all the definitions, all these definitions along with some example. So by keeping by keeping these elements in mind, we are going for next topic. That one is derivation of torque. So we need to derive the expression in exam point of view. In exam point of view, we need to derive the expression of torque, which is happen in electromagnetic induction type relays, which is happen in electromagnetic induction type relays. Okay, let we see it step by step how we are going to derive the torque equation of those type of relays. So let here see, this one is the simple example how we are going to derive it. So here in this diagram we can see some arrangements like it is a C type, it is a E type, it is a E type electromagnet, and bottom also we U type electromagnet we placed it, and these two magnets have two windings, like one winding we call it as a primary winding, and another winding we call it as a secondary winding. Okay, that means here in this case simply we divide a single phase. That means we split a single phase into two phase. We split single phase by using this structure into two phase. Okay, this single phase, that means here this particular winding get supply from the secondary of current transformer, and this one is the single phase. Let assume it is a single phase supply. So single phase supply, and now by using this structure, we are going to split this single phase into two phase. That means here we get I1, and also we made it one more current. That one is I2 value. Because of this I2 we can get because of transformer action. So one more important thing, the winding, that means primary winding and secondary winding have different resistance and reactance characteristics. That means this winding and this winding has a different resistance and reactance values, so we need to keep it like that. That's why only we can get two currents with phase difference. That's why only we can get two currents with phase difference. So I1 and I2 also we can get because of transformer action, and this I2 is not in phase with I1. So there is a phase difference. Between I2 and I1, and we are providing because of these two windings have different resistance and reactance values. Okay, we can see clearly I1 and I2. So already we know that when the current carrying conductor is there, that current carrying conductor produces a flux. So here we can see two current carrying conductors. That one is first one, primary one, and second current carrying conductor is this one. Okay, so first conductor carries a current of I1, and second conductor carries a current of I2. So both are produce flux. In air gap, but there is a phase difference between this winding flux and this winding flux. So we assumed it. we assumed it like this. By using this phasor diagram, we can clearly understand. So this one is the phasor diagram. This one is the phasor diagram. So here, by seeing this phasor diagram, we can say what is going on in that diagram, in that previous diagram. Let's see. So here it is pi 1 flux. This pi 1 is because of I1 current, and I1 already we know that we can get from a current transformer. Now pi 2 is because of I2, and I2 is because of transformer action in the structure. In the structure, because of transformer action, I2 is happen in winding, and because of that I2, pi 2 is developed in air gap. Okay. Now there is a phase difference between I1 and I2, and that phase difference we consider it alpha. So in the same way, we know that flux is directly proportional to current, and also flux is in phase with current. So with that knowledge, we can draw two phasors. Those are pi 1 and pi 2 phasors. Here in this case, we take it pi 2 is lead pi 1. Pi 2 is lead pi 1 at an angle of alpha. Let's assume the phasors are moving in anti-clockwise. Let's assume the phasors are moving in anti-clockwise. At that moment, that pi 2 is lead pi 1 with an angle of alpha. Now, so these two fluxes are alternating fluxes. Am I right? Yes, these two fluxes are alternating fluxes, and these two fluxes are linked with disk. What is there in air gap? What is there in air gap? The disk is linked with these two fluxes, and flux nature is alternating flux. So because of that, two EMFs are induced. Two EMFs are induced in disk. So those are E1 and E2. Those are E1 and E2. Here E1 is because of the rate of change of flux 1, pi 1, and E2 is because of the rate of change of pi 2. So here it is E1 is lag pi 1 at an angle 90 degrees. So already we have some idea about phasors, basic phasors. So always voltage is lags pi 1 lags flux at an angle 90 degrees. So on the basis, here we can draw a new phasor. That one is E1. That E1 is lags pi 1 at an angle 90 degrees. In the same way, because of pi 2 also, EMF is induced in disk. That phasor, that induced EMF, we name it, that one is E2, and that E2 is lags pi 2 again 90 degrees. This one is the 90 degrees value. So we can see two EMFs in disk at a time. We can see two EMFs in disk at a time. That one is E1 and E2. E1 is because of pi 1 and E2 is because of pi 2. Now what happened? What happened when EMFs are induced in a disk? So immediately we can see it. A disk is nothing but a closed one. Disk is nothing but a closed material. That means eddy currents are occur because of these EMFs. Eddy currents are occur because of these EMFs. So because of E1, I1 current is circulated in disk, and because of E2, I2 current is circulated in disk. Okay. So here we take it assumption that one is simply we neglect self inductance of the disk. Here in this case, for for simple calculation, for simple phasor diagram, we take one assumption. That assumption is the self inductance of the disk is negligible. So this one is the assumptions what we took. Okay. So based on that assumption, that I1 is in phase with E1, and I2 is in phase with E2. Here it is I2. Okay. So here it is I2. I2 is in phase with E2, and I1 is E1, in phase with E1. Now we can see elements, like we can see the elements, electromagnetic elements like pi 2 and pi 1. It is there in air gap, which link with a disk, and E2 and E1. So these are there in disk because of flux cutting, and because of E1 and E2, we can see in disk I1 and I2. Okay. Now we can see I1, I2, pi 2 and pi 1. So already we know that we can get electromagnetic torque. We can get electromagnetic torque because of flux interaction, because of two fluxes interaction. So we can develop electromagnetic at the case only. That case is because of two magnetic flux interactions. Two magnetic flux interactions. Here let's see. Here let's see, this I1 is already in DC motor. We can write one equation. That one is T value is equal to DC motor torque value is equal to that means directly proportional to T is directly proportional to pi into Ia, pi into Ia. Okay. So on the same way, in the same way, here also we can write it. Here it is the current. Here is the I1 current, and this I1 current is interact with pi 2. Here I1 current is interact with pi 2. In the same way, I2 current is interact with pi 1. I2 current is interact with pi 1. That means because of these interactions, we can see two torques. We can see two torques on the disk. So first torque is because of I1 is interact with pi 2, and second torque is because of I2 is interact with pi 1. In the same like a motor, electromagnetic motor, that means induction motor or a DC motor. So that T value is directly proportional to I into pi. Here I is I1, pi is nothing but pi 2. And here I is I2 and pi is nothing but pi 1. So two forces or two torques. One torque is because of I1 and pi 2. So we can write it that the torque value is directly proportional to I1 and pi 2. In the same way, we can observe one more torque. That one is I2 is, that means the torque is directly proportional to I2 into pi 1. So with this knowledge, we are going to derive the torque equation of electromagnetic induction relays. Okay. So with this knowledge only, we are going to derive the torque equation. I hope you can understand. You understand this one. If you understand the phasor diagram, definitely you can easily understand the equation of torque. Okay. So by keeping this in mind, we are going for the equation, torque equation, derive the equation of torque. So here it is. Here it is. So because of split phase, because of structure, here we can see two fluxes. One flux is pi 1 and pi 2, and pi 1 is from I1, and where I1 get from the current transformer, and this pi 1 instantaneous value is pi 1 m sine omega t. So here it is. So these two are these two are alternating fluxes. That's why here we write pi 1 is equal to pi m sine omega t, and pi 2 is already I told you at the time of phasor diagram. At the time of phasor diagram, already I told you pi 2 is leads pi 1 with an angle of alpha, because both the windings are different resistance and reactance, that's why these two has phase difference. Now these two fluxes have same frequency. So because we know that why these two fluxes are same frequency, with knowledge of transformer, working principle, we can say it, these two frequencies, these two element frequencies are same. Okay. Now phase difference is alpha, already I told you, that means pi 2 is leads pi 1. Now, so here it is, the link here E1 value, that means EMF, which is induced in disk because of pi 1. So the pi 1, that means link with this pi 1 is linked with a disk, and that pi 1 nature is alternating. So the link disk link with this flux is always changes. The flux, sorry, flux is always changes with which link with the disk, and E2. Here E2 is directly proportional to d pi by dt. E1 is directly proportional to d pi 1 by dc. So this one we get from the Faraday's law, Faraday's of electromagnetic induction law. Okay, what is the Faraday's law of induction? That means like so whenever we are provide a relative time variation between conductor and magnetic field, automatically EMF is induced in current. Here the time variation is nothing but flux is going to change with respect to time. So based on that, here we can write two equations, E1 and D2. E1 is directly proportional to d pi 1 by dt, and D2 is directly proportional to d pi 2 by dt, p pi 2 by dt. Here dt is not visible, so please try to understand. It is directly proportional to d pi 2 by dt. Now these induced EMFs are again produce currents. So those are I1 and I2. So already we take it assumption, that means the disk has no self inductance. That's why I1 is in phase with E1, and that I1 is directly proportional to d pi 1 by dt. I2 is directly proportional to d pi 2 by dt. So based on that, here we write it like now, where I1 and I2 are the eddy currents or circulating currents, no problem, whatever it may be. We can write eddy currents or circulating currents. Okay. Now we substitute in this equation pi 1 and pi 2 instantaneous values. Pi 1 and pi 2 instantaneous values we can submit in this equation. Then we can get I1 and I2 values in terms of this one. So here we can get I1. I1 is directly proportional to pi 1m cos omega t, and I2 value is, this one is I1 value. This one is I1 value. So here we can get I1. That value is directly proportional to pi 1m cos omega t. In the same way, we can get I2, and that I2 is directly proportional to, after submitting pi 2 value, substitute the pi 2m, pi 2 instantaneous value, we can get I2 is directly proportional to pi 2m cos of omega t plus alpha. So this one is the two equations. Now we get two currents. Now we get two currents which are produced in disk. Those are I1 and I2, and also we find the values. We find the I1 and I2 values. One value is pi 1m cos omega t, and another value is cos of omega t. That means pi 2m cos of omega t plus alpha. Okay. Now by using those details, by using these details, we are going to calculate the force which is developed in disk. So already I told you in disk two forces are produced. Two forces are happen on disk. One force we take it one F1, and another force we take it F2. Force or torque, whatever it may be. Okay. First force is because of interaction of pi 1 and I2, and second force is due to interaction of I1 and pi 2, like what we see in electromagnetic motors, like induction motor and DC motor. So torque is directly proportional to pi Ia, where it consider DC motor. Okay. In the same way, here also torques are developed. One torque is because of this interaction, and another torque is because of this interaction. So ultimately we can see two forces on disk. First force is F1 and second force is F2. Now next point, these two forces are acting in the opposite direction. This is very important. So two forces are happen in disk whenever we are providing a current from the CT, and the produced forces are in opposite direction. So we can get this one by using Fleming's law. By using Fleming's law, we can identify the force directions, and those directions are exactly opposite to each other. If you try it, then you can get understand. Okay. So by using Fleming's law, please try it, and definitely you can get answer, and that answer is both the forces are opposite to each other. Okay, try it. Now, hence net force on a disk is proportional to the difference between the two forces. Here two forces are developed, and these two forces are opposite to each other. Now the net value, net force, the net torque on disk is equal to difference between these two forces. So here I write F, the net force on disk is directly proportional to F2 minus F1. Net force is equal to F2 minus F1. Because of this net force only, disk is going to rotate. Because of this net force, and this net force is directly proportional to F2 minus F1. Here already we know the value of F2 and we know the value of F1. Here the F2 value is pi 2 I1 and F1 value is pi 1 I2. Okay, so by using this information, we are going to calculate F is nothing but net force, or in place of F we can write torque also. Okay, so net torque or net force is directly proportional to pi 2 I minus pi 1 I2. Here in place of pi 2 we can write, instantaneous value, that means pi 2 m sin omega t plus alpha, and I1 already we calculated I1 value, and that I1 value is here. We calculated that I1 value is that I1 value is this I1 value is pi 1 m cos omega t, and I2 value is pi 2 m cos omega t plus alpha. Directly we substitute these values in this equation. Then finally we can get F value after simplifying the equation, after solving this equation. Finally we can get F value, net force value. That net force value is equal to pi 1 m pi 2 m sine alpha. This is the final solution of torque. So net force value is equal to pi nm pi 1 m pi 2 m sine alpha, where alpha is the angle between pi 1 and pi 2. So these two are maximum values. Pi 1 m and pi 2 m is the maximum values. Okay, so alpha is the angle between pi 1 and pi 2. Okay, now that means force is depends on angle also. Angle in between pi 1 and pi 2. If alpha is equal to 90 degrees, then this F value becomes maximum. When alpha is equal to 90 degrees. When alpha is equal to 90 degrees, we can get maximum torque. Now, if alpha is equal to 0, what happened? If alpha is equal to 0, the net force on disk is equal to 0. That means if we are not providing any phase angle between two fluxes, ultimately the torque availability on disk becomes 0. So to get torque, we need to provide phase angle. Otherwise, no torque on disk. Okay, that's why we can say it. We need to use split phase. For producing torque. Here we get equation of torque, that means equation of force. That value is directly proportional to pi 1 pi 2 sine alpha, where alpha is the angle between pi 1 and pi 2, and this force is going to be maximum when alpha is equal to 90 degrees. This force is equal to 0 when alpha is equal to 0. Now in this equation we can substitute RMS values. In place of pi 1 m and pi 2 m, we can substitute RMS value. After substituting the RMS value, finally we can get net torque is equal to that means directly proportional to some constant. Is there, and that constant depends on structure constants. Okay, so F is directly proportional to pi 1 and pi 2 sine alpha. This one is the torque equation of electromagnetic induction type relays. Okay, electromagnetic induction type relays, the produced torque on movable element, either it may be cup type or disc type, or cup type, whatever it may be, the produced torque value is directly proportional to pi 1 pi 2 sine alpha. This is the equation. This is the derived equation of torque of electromagnetic induction relay. So keep it in mind and try to learn it. This is very important for exam point of view. It is very important, and try to remember this equation. And that torque equation is directly proportional to pi 1 pi 2 sine alpha. In place of pi 1 and pi 2, we can write it I1 I2, no problem, because I1 is directly proportional to pi 1. Okay, so based on that, again we can write F directly proportional to I1 I2 sine alpha. I1 I2 sine alpha. Okay, here we can use only one source. Here we use only one source for producing magnetic field. Okay, that's why here we write I1, I2 sine alpha. Suppose if we are going for two sources, suppose if we are going for if we are going use two sources for production of production of magnetic torque, for production of magnetic torque. If we use two sources, at that case this force is directly proportional to vi sine alpha. Vi sine alpha. Okay, so vi sine alpha is the torque expression when we are using two sources for production of torque. Okay, so that means we get one winding. We use for one winding. We use for second winding. So okay. So at that case, I will explain it later why we are going to take Vi sine alpha. So when we are using two sources for production of magnetic torque. Okay. So here up to now, please try to remember this one is the torque equation. That torque is directly proportional to I1, I2 sine alpha or pi 1, pi 2 sine alpha. Okay. Now, so by keeping this one, we are going for electromagnetic induction type relays. Electromagnetic type induction type relays. So already we know that we have different type of induction relays, electromagnetic induction relays. So those are induction disk type, and induction cup type. And okay, in our syllabus we have two type of electromagnetic induction relays. First one is disk type relays, and second one is cup type relays. Okay, in both the type of relays, torque equation is same. The torque is directly proportional to I1, I2 sine alpha. Okay, now let me see it how induction disk type relay is going to operate, and how induction cup type electromagnetic induction relay operate. Let me see it. Here it's see. First point. So the electromagnetic relays operate on the principle of split phase. On the principle of split phase. Am I right? So because we are going to provide two fluxes with phase difference. We are going to provide in air gap two fluxes with phase difference. That's why we make arrangement. That one is split phase. Split phase. Okay. So like induction motor, like a single phase induction motor. Okay. Now the initial force is developed on a moving element. The initial force is developed on the moving element. That may be a disc or another form of the rotor of the non-magnetic moving element. Okay. Now, rotor part is maybe like a disc shape or cup type, whatever it may be, no problem. So due to the produced torque, disc, either it may be a cup going to rotate in air gap freely. Now, the force is developed by the interaction of electromagnetic fluxes with eddy current. So already I told you I1 is interact with pi 2 and I2 is interact with pi 1. So because of that reason, electromagnetic torque is developed on surface of disk. Okay. So that induced in the rotor by these fluxes. Yes, correct. Now, the different type of structures have been used for obtaining the phase difference in the fluxes. So to provide phase differences, we are going to use different structures. That one is shaded pole structure, and wattmeter or double winding structure, and induction cup type structure. Okay, so here we can get split phase. Here we can get split phase because of different structures. Those are a shaded pole structure, and watt meter or double winding structure, and induction cup type structure. So we see it one by one. So how these structures are going to provide torque on disk. Torque on disk. First, we can see it shaded pole structure type. Shaded pole structure type. So, so this one is the shaded pole structure. Here also we can see one winding. So this one we call it as relay coil. This is, we call it as relay coil, and this relay coil gets supply from current transformer. Am I right? Yes, this relay coil gets supply from current transformer. Now, so it is alternating current. So current transformer send a alternating current to the relay coil, and due to that relay coil, flux is developed, alternating flux is developed. Here at this section we can see different fold tips. Here we can see two type of fold tips. So here it is one tip, and here it is another tip. And here for this tip we are making an arrangement. That arrangement is simply we arrange a band. We put a band to the tip. So here we place one copper band, simply call it as copper band. Here we place a copper band to the tip, and it is in this tip we are not going we are not making anything for this tip, and here we are placed one copper band. Okay, that's why we call it, it is a shaded tip. That's why we call it as shaded tip or copper band tip. So it is unbanded tip, it is banded tip. Okay, and in this diagram we can call it, call it as copper band tip. We call it in this diagram shaded ring tip. It is unshaded, tip, it is shaded tip. Now what will happen when we arrange a copper band to the tip? So what will happen when we are going to arrange to the tip? So already we know that, so here this particular pole have alternating flux. This particular pole have a alternating flux. So when we place a copper band to this tip, that copper band is linked with alternating flux. This copper band is that means this alternating flux. The alternating flux is linked with the copper band. So when the alternating flux linked with the copper band, what will happen according to Faraday's? Whenever the flux linked with this copper band is changed continuously with respect to time, EMF is induced. In this copper band, and that induced EMF is opposed. That means that induced EMF is opposes the change in main flux. Simply we can say it Lenz law. Based on Lenz law, we can say simply. So according to Lenz law, already we know that Lenz law statement. That one is according to Lenz law. What is that means? So here it is. Induced EMF. Here it is induced EMF, and the reason of induced EMF is this alternating flux. So this induced EMF, the induced EMF direction in this copper band is like that one is that induced EMF direction is always changes, always opposes the change in alternating flux. Okay. So according to Lenz law, we can say it. The Lenz law statement is the effect is always opposes the change in cause. Am I right? So am I right? Lenz law statement is the effect is always opposes the change in cause. Here the effect is induced EMF. And cause is alternating flux. So the effect, that means induced EMF, is always opposes the change in cause. Here the cause is alternating flux. Because of that there is a phase difference. Between fluxes which are available at both the tips. Here the available flux at tip 1, we call it as pi u. That is nothing but flux from the unshaded one. Flux from the unshaded part. Now here we can see one more flux. It is from shaded tip. That's why here we put a symbol pi s. Pi s means flux from the shaded pi u from the unshaded. So I repeat once again why pi u and pi s have a phase difference. Why pi u and pi s have phase difference? Let us explain step by step. So when we are placing a band, copper band at this tip, this copper band, because of this copper band, an EMF is induced, in this copper band, and that EMF is opposes the alternating flux effect, and that opposing nature we can explain with the help of Lenz law. And Lenz law statement is the effect is always uh, opposes the change in cause, here the cause is alternating flux, so effect is induced EMF, and this induced EMF opposes the change in alternating flux. That's why here the pi s is lagged, the pi s is lagged pi u, because the induced EMF in this copper band is opposes the change in cause. Here the change in cause, that means cause is pi u, and one more important thing, the magnitudes at this tip and at this tips are not same. Pi u and pi s magnitudes are not same because of direction of magnetic flux. Here we can see at this tip two fluxes. Here you can see two fluxes at this tip. One is because of copper band, and another one because of pole. So these two fluxes are in opposite. These two fluxes are opposite at some case, and equal at some case, and same direction at some case. So that's why these two magnitudes are not same. And one more thing, these two fluxes are not in same phase, because of Lenz law action, statement we can say it. Because of Lenz law statement, by using Lenz law statement we can say it confidently. That one is that pi s is not in phase with pi u, because the copper band flux or copper band induced EMF is opposes the change in cause. Here the change in cause is main flux or main voltage. Okay, now, so now by seeing this phasor diagram, we can explain. So here we can observe two fluxes. Here we can observe two fluxes. One is pi u. This one is the main flux. Because of relay coil current. We can see pi u. And now one more flux we can see. Because of shaded tip, and that one is pi s. Here pi s and pi u are not in same phase, because of Lenz law. Statement, based on Lenz law statement, we can say it that pi s is not in phase with pi u, and also magnitudes of pi s and pi u is different. Okay, so based on that, again Lenz law. Here let assume alpha is the phase difference. Between pi u and pi s. Okay, this one is the resultant flux. Of pi u and pi s is pi. Okay. Now, so two fluxes are available at this disk. That means these two pi u and pi s fluxes are linked with the disk, and because of that action, again we can see two EMFs in a disk. That one is EU. So that one is first EMF is EU, and second EMF is ES. So this induced EMF is because of this one, because of pi u. Here we can see EU in this because of pi u, and this EMF is lags pi u at an angle 90 degrees. Already I told you, always EMF is lag. Always EMF is lag flux at an angle of 90 degrees. In the same way, induced EMF because of flux is also lag pi s at an angle 90 degrees. 90 degrees. Now, so for this disk, we are not taking any assumptions. For this disk, we are not taking any assumptions. Because of that, uh, whenever EMFs are induced in disk, we can see the circulating currents or eddy currents in disk, and those currents are IU, unshaded current, and second one is shaded current. And this IU is because of this IU is lags. This IU is lags EU. This IU is lags. That means the EU is nothing but induced EMF in disk. IU is nothing but current, circulating current in disk. So that IU is lags V EU at an angle of beta. At an angle of beta. And here, this one is the IU. This one is the IU, and this IU is lags U. EU at an angle of beta. In the same way, IS is also produced in disk, and that IS is lags ES at an angle of beta. Okay, so when two currents are occur in disk, when two currents are happen in disk, so this is is interact with pi u, and this IU is interact with pi s. Am I right? So this this disk IS current is interact with air gap flux pi u, and this disk IU current is interact with air gap flux EU. Because of this interaction, because of this flux and current interaction, again two torques or two forces are produced, two forces are available on a disk. Those we call it as F1 and F2, and F1 and F2 are in opposite to each other, so that net force value on disk is equal to F2 minus F1, and or F1 minus F2, order it may be. So F1 minus F2, or we can take it F2 minus F1. Okay.
Yes,
so
sir.
based on that condition, so negative torque or positive torque, negative torque, either may be negative torque or positive torque, whatever it may be, the net value is equal to F1 minus F2. So when net torque is available on this disk, and that value is equal to pi 1 pi 2, here in place of pi 1 we can write it pi u, in place of pi 2 we can write it pi s sine alpha, where alpha is the angle between pi u and pi s. Okay. So due to that force, the disk is going to be rotate. The disk is going to be rotate.
టైం అయిపోయింది.
సార్
టైం అయిపోయింది.
టైం అయిపోయింది సార్. ఓకే ఓకే. సో
158 అయిపోయింది.
ఓకే సార్. ఓకే, క్లోజ్ చేస్తాను సార్. In the same way, whatever meter structure also provide torque on disk. So this structure also develop torque on disk. Same what I explained in previous manner. Now this one is the induction cup type. Here important thing is, so this one is the rotor, and here the rotor structure is stationary, but the winding which is placed in rotor structure, that is nothing but, here it is indicated with black color. So the black color is indicate winding of rotor, and red color is indicate structure of rotor. So structure of rotor is stationary, and winding of rotor is going to be movable element. Winding of rotor is movable element, that we call it as cup. Rotor. Okay. Now, so it is most closely resemble induction motor, except that rotor iron is stationary, and rotor conductor portion is going to free rotate. The cup structure look like a hollow cylinder. Okay, that's why we call it as a cup type of magnetic relays, induction cup type of magnetic relays. Okay. So okay students, I will continue in next class. Today I will stop the class. Okay.